Bom dia, pessoal. É um prazer ter todos vocês aqui. Hoje nós temos um seminário especial, né? Mais um, né? Nossa lista de seminários desse semestre tem sido muito bacana. Hello, everybody. We are here in another edition of our number theory seminar. Today we have the pleasure of having Jörg Brüdern with us, professor from Göttingen, and he's going to talk about Taxicab numbers, 2 stories and 1 theorem. Thanks, Jörg.
Thank you, Hema. It's a great pleasure to be in Brasilia again. Unfortunately, only virtually. So I have to invite you to my office, but also only virtually. I was told in advance that most of my audience will be early career researchers. So I opted for a survey talk, an invitation to number theory, and to the use of harmonic analysis to solve problems in number theory. Our taxi driver wants to take us to the land of cubes and remember the taxicab number 1729. So most of the talk will be on sums of 2 cubes, and they're generically related to these taxicab numbers, that I will define momentarily. So let me first start with the sums of 2 cubes. So we are interested in those natural numbers n that can be written as the sum of 2 positive cubes. It's important to have them positive. So I'm interested in those n where n is x cubed plus y cubed, with x and y a natural number. And for me, a natural number is positive. So 0 is not a natural number for me. Otherwise, the definitions in this talk are slightly wrong. Doesn't really change life so much. But this particular sequence, those numbers that can be written as the sum of 2 cubes, I call curly S. Maybe in your elementary education on number theory, you've studied sums of 2 squares. So you just delete the cubes here and make them squares, and that's a very classical theme that even in the very old days, like Fermat, 17th century, and even those days, it was known that you can decide whether a number is a sum of 2 squares if you know the prime factorization of n. For sums of 2 cubes, no such description is being possible. So somehow the sequence of the numbers that are sums of 2 cubes is sparse but very random in a sense. Some of the questions we wish to study are also related to how often is a number representable as a sum of 2 cubes. So this set curly S could also be described as the set of all natural numbers where I have at least one such representation. So in the initial part of the talk, the main questions I'm interested in is what can we say about this set S? How many elements, for example, are in this set S if I truncate it at capital N? So number theory could also be called the art of counting. So can I count the elements in S? And when we go on, what can we say about this number R of n? And many numbers will not be the sum of 2 cubes when R of n is 0. So that's a boring result. But if it has one such representation, can it happen that it has many? So how large is R of n? And how large is it not only individually, but also on average? Well, in particular, these questions about R of n have elementary, but also very non-elementary answers. So let me start with these, and then I come back to this problem to say something about the set curly S rather than the function R of n, which turns out to be slightly more complicated. So the size of R of n, how big is this? Well, let's assume the number n is such that R of n is not 0, because if it's 0, then we know the size. So it has at least one representation x cubed plus y cubed. But then if that happens, the sum of two cubes I can factor into x plus y and a quadratic term, which is x squared minus x times y plus y squared. So it happens that if n is the sum of the two cubes, x cubed and y cubed, when x plus y is a factor of n, and the cofactor is also given by x and y. So if I want to know how many solutions there could be, then in particular x plus y divides n, and also x squared minus x times y plus y squared divides n. So if n is given, then I can factor it and can try to write the factorization. One of the factors is x plus y, and the other is x squared minus x times y plus y squared. But if I know x plus y and this quadratic term, then I can compute x and y from it. Therefore, there can't be more representations when n has divisors, because if I have a divisor, that must be x plus y or the other one. So I get an upper bound by d of n, and as you probably know, the divisor function is not very large. The number of divisors is bounded above by an arbitrarily small power of n. So you can fix this epsilon, and then in the symbol there's a hidden constant depending on epsilon. So what you should remember for most of the talk, that this R of n isn't very large. But we come to the point that it's also not always small. Well, if I have data and I don't know and they look a little bit random, I can smooth them out by looking at the arithmetic mean or the linear average. We can just sum R of n to get a rough idea how big this R of n is. And there is a very simple argument here. That is often attributed to Gauss, but I'm sure it has been known before. So if I sum R of n, what happens? So R of n means count the solutions of n is equal to x cubed plus y cubed. If I'm now summing over small n, then only the condition that x cubed plus y cubed is less than capital N remains. And x and y have to be positive. So what can we do? We can draw a picture. The area that x cubed plus y cubed is less than n is indicated here. It roughly looks like a quarter of a circle. But since we have cubes now, it's not like the circle that I try to indicate here. It's a little bit flatter here and a little bit curvier near the diagonal. So it looks roughly like a, well, not like a rugby ball. It's still symmetric to this axis because you can flip x into y and nothing changes. And this is roughly how it looks like. So now the Gauss idea was, if I should count all the points with integers, with integer coordinates that lie inside this, well, I can draw them in here. And with each of these lattice points here, I associate a small square where the side length is 1. And the point that I want to count is at the upper right corner. So that this point here that is now indicated belongs to this square where the cursor now is. And this point here, where the thumb is associated with this square. So if I do this with all the points, and n is large, then I see a figure made from these red little squares, but looks very similar to this object here. Sometimes maybe this object stretches out a little bit to the right, but you can't be any further away than just the diagonal in such a small square, and the diagonal has size √2. So rather than counting the points, I can just measure the area, and that area is easy to compute. And the error that I make, well, you can actually see you only have to follow how long is this path, because all these little squares will be only at most √2 away to both sides. So you have a small strip that is roughly the area where the cursor now covers when it travels from one end to the other. And the total of that area is just something 2 times the length of this curve. And the length of this curve, you can easily see, is roughly 2 times n to the 1/3. So the error that I get in this, by replacing the number of integer points in this figure, by replacing this by the area, is O of n to the 1/3. And the area is easy to compute. It's a constant times n to the 2/3, as you might guess, because there's a square inside here that is roughly of size n to the 2/3, and a square around this that is a little bit bigger. And you can compute this constant c is actually the area of x cubed plus eta cubed less than or equal to 1. So a small figure that sits here, and this guy is just a blown up region. One can compute this area explicitly in terms of a gamma function, but the important thing for us, this is a positive constant. And you remember this constant, this symbol C now gets frozen for the rest of the story. So whenever I write a capital C somewhere, I mean this number that comes from this linear average. So what does this tell us? I mean, if we would have that x cubed plus y cubed is always distinct except for the simple thing of exchanging x and y, then we would expect that a half times the n to the 2/3 of these numbers are actually sums of 2 cubes, approximately. But I don't know this yet. I don't even know whether R of n is bounded. And my claim is probably it's not the case that R of n is bounded. But we have already noticed that we can flip x and y. And if I have one solution where x and y are different, then I can just flip x into y and vice versa, and get another solution. Both of them get counted by R of n. So typically we expect that R of n is even. But it can happen that I cannot flip x and y. This is when they are the same. But if x and y are the same, then I can just call this number xk and see that n has to be a very special number. It's 2 times the cube. And 2 times the cube means the number of choices for k that I have where 2 times k cubed is less than n is also only of size O of n to the 1/3 as we see it here. So with very few exceptions, we already see at this stage that R of n will be an even number. So that gives me the option to define a taxicab number as one that has R of n bigger than 2. So if R of n is bigger than 2, then there are 2 genuinely distinct representations of a number n as the sum of 2 cubes. So, and by genuinely distinct, I mean that I consider solutions that I get by flipping 1 into 12 and 12 into 1 as the sign. And such numbers do actually exist. So this is the number that was the taxicab number on the title page, 1729. And one representation is sum of 2 cubes. I guess everybody can guess immediately, because this is 1000 plus 729, And 729, of course, is 9 cubed, and 1000 is 10 cubed. But it's also 1 cubed plus 12 cubed. And, well, you can now check through all these numbers. It's not, this number is relatively small, cubes grow relatively fast. Each of the two components, none of the components, because there's a 1 here, none of the components can be bigger than 12. So you only have to check for y the numbers up to 12 and see whether there is another representation, but there is not. And hence R of 729 is 4, a taxicab number. So why do we call that a taxicab number? Well, this is the modern non-stylish way of naming mathematical objects. Perhaps you've heard of a famous Indian mathematician, Ramanujan, who was an autodidact, never had university training in mathematics, but had brilliant ideas. He made many errors, but he also had brilliant ideas, but nobody understands where he got the intuition from. And late in his life, he was living in Cambridge, in the UK, and he felt ill with tuberculosis. And his mentor Hardy visited him at the hospital. And he took a taxi. And the taxi had the number plate 1729 on it. Those days, I mean, it's now it's in the 1920s roughly, even in 1990 maybe. Those days there were very few cars even in London, so such a simple number plate was the case. And Hardy was a little bit afraid when he saw Ramanujan. I said, well, the taxi had the number 1729. I guess that's quite a dull number. And Ramanujan's reply was, no, it's not. It's the smallest number n and has a representation as sums of two cubes in two different ways. So in fact, that's the smallest number where this phenomenon occurs. Sorry. So we have here another example. These numbers that I wrote down here, 6 different numbers, sums of two cubes, are not at all different. Indeed, these numbers are equal. So for the number given by each of these lines, the function R has the value 12. So, and there are taxicab numbers where R is 24 even, but I don't know whether larger taxicab numbers actually exist. My guess, however, is that R of n is unbounded. I said this before. So the deepest question that I want to pose today is, how many taxicab numbers are there? This problem is open. And I want to show you a method that makes a prediction, and we will learn what I believe how many taxicab numbers there should be, at least roughly. So first I claim taxicab numbers are fairly sparse. I denote by T of capital N the number of small n where R of n is bigger than 2. So let me briefly indicate that in order to get an upper bound on the number of taxicab numbers, it is important to understand the quadratic average of a function R of n. And the idea for this, that's a little bit intricate, but it's interesting what one can do. So I want to count the n's where R of n is bigger than 2. I do this as follows. I claim it's bounded for what I've written on the right-hand side. In principle, you can forget this second term. So let us first look at this and with initial parts. So when R of n is 0, that is certainly what most of these numbers will actually have. When R of n is 0 here, so it wouldn't appear here. So when R of n is exactly equal to 2, so that would be the situation where I have essentially just one representation. When R of n minus 2 is 0, so again, with some counts with weight 0, as it should. And then there are some numbers where R of n is 1. When R of n is 1, then I have a 1 here and a minus 1 here. So this product is minus 1. This sum, therefore, counts the number where R of n is 1 with weight 1/3, but negatively. So I've corrected this with this second term. And when R of n is bigger than 2, well, then here R of n is at least 3. This factor is 1. This factor is 3 divided by 3. So all the numbers where R of n is at least 3 are counted with a weight that exceeds or is equal to 1. So therefore, this upper bound is correct. If you open that, then you get to evaluate R of n squared. And we have already evaluated the linear average. So what I now need is a result on this quadratic average. And there is a spectacular result by Heath-Brown in 1997. It tells us with the same number C that we've seen in the linear average, multiplied by 2, I get an asymptotic formula. Now remember, the linear average will C times n to the 2/3 with a better error term. So, but the error term here is only n to the 4/9. I won't say much how Heath-Brown proved this. We just import that. That's a result that depends on clever counting and a bit of algebraic geometry. If you insert this up here, then the two leading terms drop out. So from the quadratic average, I have this error n to the 4/9, and from the linear average, I have an error term n to the 1/3, which I have here anyway. So that's what I did here already. Yeah. So remember that the R of n where R of n is 1. That's odd values of n. So we already know there could be only n to the 1/3 of these guys. So the upshot of this computation is that the number of taxicab numbers is bounded by n to the 4/9. So taxicab numbers are not very frequent. So now let's see whether we can address the numbers that are sums of two cubes without multiplicity. Yeah, so let me try to explain what goes on. So the linear average of R of n is now dominated by those numbers where R of n is equal to 2, I claim. Because what I can do is, well, if R of n is equal to 2, then I can just replace R of n by a factor 2 and count these numbers. I can do the same thing when R of n is 1. So that's an object that we had before already, and that is sparse. And the other numbers are just given by R of n is bigger than 2. But when R of n is bigger than 2, then it's a taxicab number, and R of n itself is bounded by an arbitrarily small power of n. So we get that error. Well, since this guy here is also bounded by O of n to the 1/3, what we now see is that the number of n where R of n is equal to 2 is just half, that this is factor 2, times the linear average of R of n with a small error. So I can compare the numbers where R of n is exactly 2. So that's a standard sum of two cubes. And that's 1/2 of a linear average. So I have a nice result because I want to count the numbers in curly S, And that's the same as where R of n is greater than 1. So I can write S of n is the numbers where R of n is 2, where R of n is 1, and where n is a taxicab number. Just split that. And this guy is small, we know. This guy is small, we know. And that guy is, by the previous calculation, a half times the linear average. Since we know the linear average, we have no problem. S of n is a half times c times n to the 2/3 with a small error. So what's the moral of this corollary? We've now understood sums of two cubes in the following sense. Up to capital N, there are about a half c n to the 2/3 such numbers. And if I pick one such number at random, one of those that have such a representation, then with probability 1, I will have picked a number where R of n is equal to 2. So where you only have one genuine representation and the other comes from just switching x into y. So now, what do I believe about these taxicab numbers? How many are there? That was what I said is the most interesting question. And in its weakest form, I claim this is not optimal with the 4 names that we've used all the time. It's n to the 1/3 plus epsilon. But when I explain why I believe this, we will also see a lower bound for T of n and a refined upper bound. So let's go. So let's have a closer look about this mean square of R of n, which was so important in getting information on sums of two cubes. And what happens here is, well, I can do this as follows. I have to count how often n is written as x cubed plus y cubed. And then I should square it. So I should again count. So, and I call these numbers differently, u cubed and v cubed. So now if I sum over n, then the n here disappears. It becomes an inequality. X cubed plus y cubed is less than or equal to capital N, as we have seen it before in the linear average. But in addition now, these two sums of two cubes are the same. So again, as the linear average, I have a Diophantine interpretation. Yeah? So we have one equation and an inequality to handle. So now, of course, we are interested in taxicab numbers. Our taxicab number means that x and y is not just the equal to u and v as a set. So if I flip x and y, then maybe I can take v is x and u is y, and that's the inverse representation. So what I should do is, if I'm interested in taxicab numbers, I should remove from this count those guys where u comma v as a set is the same as x and y as a set. And I call that the diagonal solutions. So let's first see how many these are. This is basically the same idea as we had before on the previous slide. These diagonal solutions contribute to R of n squared. How much? Well, if I have these, if I have x and y or u and v determined, then for x and y I have two choices. Either I can take x equal to u, or I can take x equal to v, and accordingly for y. So it's the same as just saying it's twice only the solutions to this condition in u and v. And that's the linear average, but we already know. I've made a small error here. So that's the idea when u and v are the same. When I have an error here and we know that these guys, when u and v are the same, they contribute only n to the 1/3. So that's not important. But this first term is the linear average. So we immediately understand what this is. And now you realize where the factor 2 comes from. It comes from this possibility when u and v are determined to choose x and y in 2 ways. That's this factor 2. So the diagonal solutions are responsible for the leading term in Heath-Brown's argument. So now what remains is we should count those solutions up here where u and v are different from x and y as a set. So that's exactly summing the mean square of R of n over the taxicab numbers. And if we understand this sum, then we know a lot. If we would know how this works, then for a taxicab number, R of n is at least 3. So we see at least a factor 9 here. So this sum is therefore bigger than 9 times taxicab numbers. On the other hand, R of n itself is bounded by n to the epsilon. So the square also, because you can replace epsilon by epsilon halves and see that from above, this is also bounded by the number of taxicab numbers times n to the epsilon. So roughly speaking, except for this slight imprecision with this factor n to the epsilon, this sum that remained here is not far from the number of taxicab numbers. We get fairly close upper and lower bounds. But what is this number? Well, let me try. This comes by the so-called circle method, and I guess most of you have never seen this. That's a tool from harmonic analysis that gives you a chance to count solutions to problems of the type we just considered. And even if you don't get a result because you can't prove things, it gives you a heuristics, which in all cases I know, whenever something was proved, was consistent with the predictions of this method. So it seems to be a very clever tool. And as you can see in the bottom here, we will come to that, the method just has this 100th birthday. So we applaud. So what do we do? So I've written down the counting problem from the last slide for you again. And we are only interested to count these things with this condition on the set of x and y being different from the set of u and v. But for the moment, we can forget that. We will restore it a little later. And what I now do is I write e of alpha for the complex exponential, take the exponential function at 2 pi I alpha. So the function e of alpha has period 1. Remember that. So if I take an integer k, when we integrate from 0 to 1 over e of alpha k d alpha, well, I can interpret that as a complex counterintegral over the unit circle, modulus of z equal to 1 of z to the k minus 1, and divide out 2 pi I. Why is that? Well, in this integral, just put z as e of alpha as a parametrization. So when alpha runs from 0 to 1, z runs through this circle of radius 1. And now you can apply either an elementary argument or a residue theorem to see that when k is 0, the answer is 1, and when k is non-zero, the answer is 0. And it is this representation here where the cursor is that justifies the name circle method. Now what I do is I feed one of these blocks. The situation is completely symmetric in U and in V. I feed one of these blocks into a sum where U cubed and V cubed should be bounded by n, as is being requested here. And I write just e of alpha as U cubed plus V cubed. Or if you want to write this differently, you can just call this number U cubed plus V cubed equal to n and put R of n as a weight in here. Then you can either use this formula that I wrote down, or the Parseval relation, if you know what it is, to see that r of n squared is just the integral over the modulus of f squared over the unit interval. So now, of course, this looks like an intellectual game, but it's not worth anything. However, Hardy and Littlewood suggested a different way of evaluating this integral. So we are now properly inside harmonic analysis, and we just said, well, one can find an asymptotic expansion of this integral if one observes that a function like this funny f has peaks, so large values, at rational points, and then, because f is a differentiable function, also close by such a rational point. But these peaks fade out if q gets bigger. So only those where this fraction has a small denominator q will give large values of f. And if you're far away from such guys, then while one can actually plot such functions, it happens that typically this function f behaves like the square root of a total weight. So that would mean for this sum, the total weight when alpha is 0 is roughly n to the 2/3. That's the sum of r of n. We did this before. The square root of that, so the error should be just n to the 1/3. And that's quite small. So we would hope that maybe we can evaluate this integral asymptotically. So I will do this for you. And if you're afraid of that, then I suggest that you read a good book on the circle method and you get more familiar with this. So here is why there should be a pig. I've evaluated f at a rational point a over q. And well, that's just the definition of f. And now remember that E has period 1. Now there is a denominator here, that is q. So up here in the numerator, a times n comes with period q. So I can replace n by a residue class modulo q in which it lies. So then E of a n over q is the same as E at a times b over q. And the n's get restricted to a congruence condition, n congruent to b modulo q. And then, of course, I have to recollect all the possible residue classes. So now here on the inside, I get a linear average of r of n, but with an extra congruence condition. Well, that's not so complicated. If you do this, we have this linear average. I wrote it down again. It's the same conditions as before, but we have a congruence condition on the side. So what I do instead, I enforce that u and v are in a fixed residue class modulo q, and I call these x and y just for my pleasure. But only those where x cubed plus y cubed are in the proper residue class, because otherwise I haven't observed that condition. So now if you look at this object, you have to remember this funny figure with a small tessellation of this figure that almost looked like a circle. It's this object. Well, now the points x and v come with period q. So the tessailes now have size q times q. So I have much bigger tessailes if I make a figure like that. But then if I do this, I can just apply the same argument and get n to the 2/3 times this funny volume constant c divided by q squared for an individual such count with some error term that I just wrote down. And that's again by the same argument that I showed you. The diagonal now in this tessile has size roughly a constant times 1 over times q. So this is why I'm losing 1q. And I'm still summing over the x and y's. but they count solutions of a congruence. That's elementary number theory. And the number of these solutions of this congruence, so basically this sum weighted with 1, I call rho of Q comma n. Well, if I do this, then I can refeed this result into up here and get an evaluation of f at the rational point. And there is still this n to the 2/3 and a good error term. But the n to the 2/3 now gets multiplied with this funny object here, but it's a Gauss sum. And it happens that these Gauss sums in this particular case can be evaluated explicitly. So you can write down a number for this, at least the square of it, and that's all what I will need later. That's good. So now, if I go a little bit away from this A over Q, when one does this by partial summation or by the Poisson summation formula, so there is analysis to apply. And you can see that this factor C times n to the 2/3 in reality is an integral. And if you put beta equal to 0, then this term disappears and I have to measure this area. Remember, that was part of our elementary argument when Q was 1. Yeah, so this is just what happens if I shift this a little bit away, when this becomes something, a neat integral that is not hard to handle. And there's an error term, and you can see that as long as beta remains as small as 1 over n, or it's not much bigger than that, then the influence of this extra factor by comparison with this error is negligible. It doesn't actually really matter. So, except for the fact that these G of Q comma A's, I haven't written down a formula for you because it's too complicated for me to state here. But we can see that really there's a large value, n to the 2/3. Well, what one can try now is one can collect all the values at these peaks. And so I've written them down. Maybe the denominators run up to n to the 1/3 is a fairly random choice. This stuff here, when Q is at the upper end, is just 1 over n. So that's also a good choice for the width. These look random, and to a certain extent, they are random. They just work. And then I can evaluate the portion of the integral that comes from all these peaks. And this is often called the major arcs in modern terminology. So what happens is one gets here an integral. I've extended it to infinity. The error is small because the decay in beta is dramatic. And those of you who understand this sort of mathematics a little bit, this is a situation where one can easily remove the inner integral by the Parseval relation, and one gets that this is n to the 1/3 times a constant. This front factor here, in fancy language, is often called the singular series, although it's finite. And one can turn this into an Euler product, and something very strange happens here. For those of you who know the circle method a little bit better, typically this should not be divergent, but it is. And hence you have to keep it finite. But I said that the modulus of G squared I can evaluate. And if I do this, then we can see that roughly the effects of a primes congruent to 2 mod 3 and congruent to 1 mod 3 is distinct. The reason for this is, if you look at the mapping that sends x to x cubed modulo p, then for primes p that are congruent to 2 mod 3, that's a bijection. But if a number is a cube modulo p, when p is congruent to 1 modulo 3, there are 3 solutions. And hence this term for the primes p congruent to 1 mod 4 is bigger, interestingly by a factor 7 somehow. So, and well, from the prime number theorem in arithmetic progressions, roughly speaking, half of the primes are congruent to 2 modulo 3, and half of the primes are congruent to 1 modulo 3. And hence, one somehow has to take the average of 1 and 7, which is 4. So this product behaves roughly like 1 plus 1 over p to the 4th power. And therefore, we get an asymptotic formula, which is a certain constant times n to the 1/3 times log n to the 4. Interestingly enough. So now I have done something wrong in this calculation. Let me go back to this. I did ignore this condition that x and y is different from u and b. I'm not allowed to do this because if I'm forgetting this condition, then we know that this sum that appears here has size n to the 2/3. So it cannot be the leading term, what you've just seen here. But if you bring back this condition, then we do no longer have a modulus squared, but a far more complicated sum. It inherits this condition and is over 4 variables. However, these calculations with the congruences don't see this. So if you correct the calculation, which is when an order of magnitude more challenging, one still gets exactly this result. And therefore, I believe, and that is what the circle method would predict, is that the number of solutions that we are interested in is exactly this leading term here. And well, we had this comparison with the taxicab numbers. So from here, we would guess that the taxicab numbers are roughly of that size. But I claim that I can build up a theory to count taxicab numbers with another condition, namely that R of n is not greater or equal to 2, but greater or equal to 4. And then I also get some result of this type. And from that, I would expect that the taxicab numbers are being dominated by roughly this object. So there should be some asymptotic formula for the taxicab numbers, and it will also look roughly like this. I'm not swearing on this 1/4, but it should be, the number of taxicab numbers will be of size n to the 1/3 log n to the 4. So that is the first message from this talk. And now remember that in this game, it was very important for us to approximate the representations as sum of two cubes averaged over an arithmetic progression. And we already saw that it's approximately this funny number of congruents divided by q squared times what we know when we just take a and q equal to 1. And we even gave an error term, but I claim that this error term on average is much smaller. And therefore, the calculations that you saw before can be done with more precision. And here is how one actually addresses that. That's the theorem in the title, which I obtained with my friend Bob Vaughan. And the paper has just appeared. So after the seminar, people who are interested can get the DOI. So, and it says the following: if I just look at the error that comes here from comparing the interesting arithmetic data with a smooth approximation. So I write down this error term, I square it, And when I sum it over all the possible congruences, up to some upper bound capital Q. So what is this? Most of you have been in statistics or probability. Well, this is the experiment, and this is the expectation. So I take this So I say it again because the recording will stop. So it's again this funny number 2c times q times n to the 2/3. And then there is a complicated looking error term. But the important thing is when q gets near to the n to the 2/3, then this error term here dominates. And so they have a proper asymptotic formula. So this object here describes the true size of V. So what is this telling us? In mean square, the error here in star is roughly of size n to the 1/3 divided by root q. So why is that? So if I would put that as an estimate in here, when n to the 1/3 gets squared, and we get a 1 over q that gets cancelled by the sum over a. So if all these errors would be like this, then I would get a term of size q times n to the 2/3. But as soon as this error becomes larger, then I can prove that there are very few progressions a and q where this object is larger than this term. So in an L2 sense, this is the size of the error between R and that. And that's better by a factor q to the 3/2 than what we've seen before. We also have a similar result where R of n is just replaced by the indicator function of S. But then remember, R of n on average is 2. So we have to divide this object by 2 to have a proper formula, and then this 2 becomes a half. So what do these things have to do with each other? Well, the proof of this theorem, and that's the last thing I want to show you. So the proof of this goes by the circle method. And here is how this happens. Remember that this V was a square, like we see here. I can open that square when I get a term that involves this object being squared and 2 other ones. And I wrote them down here for you. It's just squaring out. My interesting term is this one, because these 2 guys are fairly elementary to evaluate. So let me see what happens here. So I have this counting term being squared. If I write down 2 copies, maybe one sum with n and one sum with m, when n and m are both congruent to a and I sum over a, so they're just congruent to each other. So now if I write this congruence as an equation, then I can have that n is equal to m. That's the mean square of R of n, I know this. Or maybe m is the bigger number, and when m minus n is positive, so it's q times another number L. So if I insert Heath Brown at the beginning, we see the leading term in our formula popping up with a good error term. And we have the remaining points where m is bigger than n, which is now coded in L being positive. And you can really see now an additive problem like the sums of 4 cubes before. There's one variable m, there's one variable n, weighted with R, and there's a product here. So I can write this interesting term, what I called B, as an integral. And it beautifully factors. It's this exponential sum f that we saw before squared, but now we don't have to integrate that over 0, 1. There's also this product term. And that is essentially a geometric sum. So it's very easy to get bounds on this. So from the major arcs, we get a neat formula, which is n to the 4/3. You can follow the same logics, times a polynomial in log n or log q or whatever you want. It's the same thing because q is log q is 1/3 log n. And this very big term that sits in there gets cancelled by the leading terms from this thing, because you see here already it's n to the 4/3 sitting outside, and it's quite easy to get that this object grows like a logarithm in Q. So it's roughly similar to what we saw before. And then all these big terms in this stuff will cancel out. This term remains, and the three error terms arise. So if you look at our paper, you will see this argument performed in some, well, technically easier, but intuitively more complicated way, but gives slightly better error terms. Okay, so that was my invitation to CubeStand. And the next time I'm allowed to talk here, I will tell you not about sums of two cubes in arithmetic progression, but taxicabs in arithmetic progression, as you can see them here. Thank you very much. And
well, thank you very much. Thank you very much. But it was a wonderful talk, a wonderful talk. And I'm very impressed with the complexity of this. I was expecting it's about 100 years old problem, and there is still a lot to do in this. And
oh yes, yeah.
But of course, I would imagine that, well, what I can change the degrees and look for different taxicab, right? Instead of yellow cab, look for blue cabs or all of.
Yes, of course you can do this. You can do this for higher powers, but unfortunately, in this game, so the theorem that I have of Bob Vaughan. So maybe I can go up here again. So if you want to write down something for sums of 2/4 powers, for example, when we don't have an analog, the point is that for sums, so somehow 2 cubes is responsible for this 2/3 here. And if I have 2/4 powers, then I have 2/4, which is a half. And it's intrinsic to our method that the error term will always be bigger than n to the 1/2 times q. So we cannot expect for 2/4 powers to get an analog of the theorem. But of course, the speculations that I've made about taxicab numbers and so on, they might also exist. But there is a famous conjecture of Euler that when you have here, if you replace the cubes by 6 powers, then there should be no non-diagonal solutions. This hasn't been proved yet. So, and let me try to get the DOI for you. So here's online first, and people this so people can copy the link if you want, and it's fortunate it's open access, so the paper should be available for you through this. But I'm afraid you should be an expert in the circle method if you want to read beyond the introduction.
But don't be afraid, isn't it? Don't be afraid.
Exactly.
Any other questions or comments? So in this final minute, I thank you again, Jörg, for this nice talk. I thank you everybody for participating on the seminar, and see you next Wednesday, if all works well.
So thank you for your interest. Bye-bye. I get back on my plane to Göttingen. And I will be there in 1 second. Bye-bye.
Thank you. Thank you all. Bye-bye.